further ado, I'd like to welcome our employee.
Thank you. Thank you so much. Well, it's a pleasure to be here. Thank you, John. And thanks to the ARMA community and those of you who are here in person or watching the recording. I appreciate the interest in geothermal. And today I was going to walk through sort of a broad overview of what geothermal is, what are the benefits of geothermal, potential for the future, what does it look like in the US right now, and then finally, what is the US Department of Energy doing to get us to that potential? And so I'll go through kind of a lot today, and feel free though to take notes of questions, and I'm happy to dive in on any of the areas in more detail at the end. So basically, and for those of you who are well aware of the basics here, what geothermal is and such, feel free to check email in that time. But I think it's really important to get everyone on the same page, because as I'll talk about during this talk, one of our biggest challenges is awareness and is an understanding of what benefits geothermal can provide and the broad spectrum of uses that it can provide. So basically, geothermal is heat from the earth. You all know that. And I love this graphic because it really shows the full spectrum of those opportunities. So you can basically, depending on how deep you're willing to drill into the subsurface, there's more and more heat. But we can still provide really useful benefits from even just superficial work. So working in the shallow subsurface at low temperatures at the bottom of the thermometer there, 40 to 80 degrees Fahrenheit, for heating and cooling homes and buildings from heat pumps. And then we kind of, in the direct use span, there are a massive amount of opportunities that are being taken advantage of in Europe for greenhouse warming, for aquaculture. People are brewing beer and distilling. There's even the opportunity for hydrogen production, which is starting up in New Zealand right now. And then, of course, at the other end of the spectrum, the higher temperature range, well, actually between 150 and 700 Fahrenheit, we can generate flexible baseload electric power, which is really important. So obviously, lots of attributes for geothermal, and the fact that basically, wherever you go, and the deeper you drill, there's heat, potentially stranded heat. Geothermal is ubiquitous, and so that, along with the fact that it's clean, that it's reliable, that it can be used across industrial, commercial, residential sectors for different solutions, makes it, I think, a really powerful and really exciting opportunity for the U.S. going forward. So, as I said, it's baseload energy, but something that's unique about geothermal is that it's flexible, and therefore it can help us stabilize the grid. And I'm going to talk about this a little bit later. It creates jobs. It can provide resilient power and cooling and heating solutions in a variety of geographies. So we can work in urban centers. You see this internationally. Many cities have heating and cooling from geothermal in Paris and in Reykjavik. But we can also work in remote communities with small modular units for power production or for direct use, as well as other rural areas. Also, there's a really interesting and unique opportunity that I'll just touch on briefly, but the opportunity to use geothermal as a domestic source of critical materials. And so that is a tremendous need in the United States right now, and can provide an economic benefit and reduce some of the costs with geothermal development, which are at this point one of the limiting factors for development. So I'll talk about these things in a little more detail in the next couple of slides. So first, just to kind of put this in the context of where I work and what the Department of Energy is doing. So all of the attributes that I just shared are really nicely aligned with the new administration's goals. And within the Office of Energy Efficiency and Renewable Energy, which is where the geothermal program sits, there are these 5 new priorities that you can see around this circle. So we're looking at 100% decarbonized electric grid by 2035, reducing the carbon footprint of buildings, of decarbonizing energy-intensive industries, the transportation sector, and then also enabling a net zero agricultural sector. And so going back to that thermometer, you can see that there's quite a bit of overlap in what geothermal can provide in this space, from lithium for transportation, from aquaculture and agriculture, greenhouse heating and cooling, or heating for the agriculture. We have massive opportunities in the heating and cooling space for reducing the carbon footprint of buildings in the US. And then, of course, the big prize, hydrothermal and EGS development, power production, helping to get us towards this decarbonized grid by 2035. So this is really exciting. And so alongside our sister renewable programs that you're all very aware of, and have the spotlight, solar and wind, we are very, very excited to help advance these clean energy goals that are set out by the new administration. And although we're not the most known renewable energy, we have this massive resource that I'll touch on again later, but basically on the order of multiple terawatts of resource in the United States. And that's why we care, why the Department of Energy cares, and why we're investing money in the development of geothermal technologies across the spectrum. So a recent study that we did, actually it's been since 2019 at this point, but the GeoVision study shows that with technology improvements, we can contribute around 8% and probably more, depending on the scenarios that we're running, with policy incentives, with technology improvements of all US generation capacity by 2050. And then 23% of heating and cooling market by 2050 as well. And so this is really exciting because of not only the contributions that we can make, but the tremendous amount of avoided CO2 that could come from those developments. So the equivalent of around 26 million cars removed from the road on an annual basis until 2050 from those numbers. So in addition to being carbon-free, there are some other unique characteristics of geothermal that I'll go through pretty fast. So capacity factor, for those of you who know what this is, forgive me, but basically geothermal can operate 24 hours a day, basically, with relatively steady output almost all of the time, and this makes it unique. So you can see on the left side there that we can generate around 2 to 4 times as much electricity as another plant that might have the same installed capacity. And I keep coming back to this term of flexible to describe geothermal, baseload and flexible. And what that means is that our utilities can benefit from the grid services that we can offer, meaning we can operate in a load following mode in addition to having and providing this baseload power that's available even when sun might not be shining. And utilities, especially in states where there's a glut of other renewables, need generation sources that can balance these daily and seasonal loads in generation. And so our operational flexibility means that we can provide a higher value than some other technologies per megawatt. So you might hear that geothermal has a higher LCOE than other technologies. That's true, but it's not necessarily taking into account the fact that there are other significant benefits. This is namely one of them. So some recent analysis that was done showed that in California, geothermal generation is actually worth $32 more a megawatt hour electric than generation from solar on a combined energy and capacity basis. So that's a really big deal. So again, it might not be the lowest cost solution on an LCOE basis, but it has the highest economic value. And we're seeing that as in new PPAs that are being signed in the last couple of years since 2019, many of the off-takers are located in California, and they're taking into consideration this flexibility that geothermal offers. And one last thing to say about it that I just think is really interesting from an engineering perspective is the way that one place where they're actually doing this and started doing this is in Hawaii, the Ormat field in Puna, where they're basically the first to at least have a PPA that is contracted to operate flexibly. Other plants have been doing this, testing it out, but they can go between around 38 and 22 megawatts operationally. So it's pretty exciting that this opportunity is finally being recognized. And I think as we see more RPSs in states, we'll see more folks taking into account the benefits that geothermal does provide. Then on the right side of this slide, just to touch on really quickly, a small, less land area and space compared to other renewables, which is also important when we're thinking about limited space in the U.S. for power generation. Jobs also. So geothermal, our analysis shows from this GeoVision report that I'll provide the link for at the end. If we advance our technology such that deployment can grow, and we can see significant new installed capacity on the order of what I mentioned, the 60 gigawatts by 2050, or 8% or so generation of U.S. generation, we could see on the order of 300,000 new jobs. And these are mostly jobs in the operation and maintenance positions related to exploration, deployment, and on-site work. So kind of following in really nicely into this space, those expertise also just happen to be the same expertise and the core competencies of the oil and gas industry. And so we are a very small industry at this time. Our market cap is significantly smaller in geothermal than the $1 trillion industry of the hydrocarbon industry. But so we can't necessarily absorb all of the jobs and all of the workers that are being displaced right now by the downturn, but the skill sets are directly transferable, and we're very eager to help transition folks that have these really specialized skills in exploration and drilling in geoscience and engineering into this clean energy industry where we really need more folks as we expand. So the last piece, just to kind of cover the exciting benefits of geothermal that you might not have known about, is the opportunity for critical materials. And so we are not normally considered a player in the world's lithium market. Most of our lithium comes from Argentina, Chile, Bolivia, but the United States Geological Survey has indicated that there are quite a bit of critical metals out in the Western US, and especially in the Salton Sea is one area of significant focus right now, a shallow lake that's in Southern California. Some research shows that there could be up to 40% of the global lithium supply just possibly extracted from geothermal brines in this area. And so not only would that be tremendous for the US controlling this very strategic market and for our battery supply chains, but this is also really important to help offset some of the costs of geothermal power plants and power and development, making it more economic and more attractive for developers. So not to say that we can do this everywhere, but there are some areas where there's tremendous opportunity in the US for extraction of critical materials. So just to put some things in context, you kind of have a sense for benefits of geothermal, and then I just wanted to really quickly go through where the domestic and the international community sit. So you can see there on the right side of the slide that around 15,000 megawatts of geothermal capacity as of 2020 in about 29 countries. Development is underway in another 50 countries or so, with massive increase in the installed capacity, probably another 10 plus installed, or 10,000, installed capacity in the next 10 or so years, with really rapid growth happening in Turkey, in Indonesia, and some other places. So, which is tremendously exciting. The US, you can see in the middle, is actually the global leader in installed capacity. And though, despite our leadership, however, we only have around 2% of renewable generation comes from geothermal in the US, and around 0.4% of total overall generation capacity. So it's very low. Around 3.6 gigawatts installed, and you can see on the left side of the slide there, those are the states where current operating plants exist. There's around 93 plants, as you see, in the Western US and in Hawaii. Some of these states are a majority or a significant portion of their power comes from geothermal. Hawaii is around 30% of total energy. California, you'd be surprised to know, is around 8%. So there's a tremendous resources in some of these states. But as I'll talk about in a minute, there are resources elsewhere that we can have the opportunity to develop, and that's something that the Department of Energy is working on. Even without those technology improvements and the R&D that we're working on, there's still a massive amount of development underway right now, 58 active projects currently working, and lots of new PPAs. As I mentioned, a lot of them are actually power that's going to California because of their consideration for this baseload flexible power. And then on the right side, you can see the geothermal heat pumps, just to give you a sense. The data is a little old there, but there's around 2.5 million heat pumps installed in the US currently, with and not pictured there on the slide, around 23 district heating systems in the United States that date back to 1892 in Boise, Idaho, where the first one was installed. So that's kind of the overview of where we are internationally and domestically. And then now I'll kind of move on to what we do in DOE. And so we are at the Geothermal Technologies Office is the largest funder of geothermal research in the United States, of course, and potentially in the world. But our priority is innovative technologies that are going to move the needle on geothermal in both the power side and in the heating and cooling side. And so we have three major priorities, and they're focused on number one, getting power online fast. We want to get to 60 gigawatts or more and we want to do it quickly. And we're doing this by working to develop and resolve these technical and non-technical challenges that are limiting deployment. So this is accessing the massive EGS resources that exist, accessing the hidden hydrothermal resources that the USGS say exist in the Western US. The second priority is decarbonizing heating and cooling loads by using direct use and by heat pumps. So space heating, again, things, I work on the power side, but it's just absolutely fascinating for me to hear that space heating and water heating in the US is 2/3 of residential energy use. So, and most of that comes from natural gas. So the opportunity here to reduce emissions by offsetting the use of natural gas, the use of hydrocarbons in general, and then also the added benefit of providing more resilient heating and cooling in, as I mentioned earlier, rural and urban environments is really exciting and really tremendous. And this is happening globally. Europeans are super focused on heating and cooling and using renewables, especially geothermal, for the reduction of hydrocarbon use and CO2 emissions. So this is a really important space. And then our third priority, which we're really proud to have as a new priority in our office, is inspiring economic, environmental, and social justice advancements through geothermal. So we really want to do better than we have been doing in the renewable and power community in general. We want to create opportunities for not only the improvement of communities that have been underserved historically, which benefits everyone, not just those communities, but we also want to bring to our community a diversity of thought and experience to help resolve our challenges. And so we're doing this by trying to encourage more diverse teams that apply to our work, and then by asking them to think about diversity and equity in the way that they design their projects and run their projects. So we're really proud and excited to be working towards these three goals. So now I'll talk kind of about the way that our office is divided. Hydrothermal program, we have an EGS program, low temperature and direct use work, and then we have a program focused on analysis that underpins sort of everything that we do. So just a quick reminder for those of you who might not know hydrothermal systems. So we are here looking at just basically a really generalized diagram of a hydrothermal system, but often we think of hydrothermal systems present where we see hot springs and geysers at the surface. We know that there's fluid impermeability and heat, obviously, that's then bringing that fluid up to the surface where we can see them in these superficial features. But we also know that there's 30 gigawatts of geothermal that exist, hydrothermal resources that don't have any surface expression. And so our hydrothermal program is focused on new methods to help us find those hidden resources and to reduce the exploration risk of accessing those. So here's kind of just a little slide on each of our programs. What are the challenges? What are our priorities? And so, as I said, we're focused on new and innovative methods to help reduce exploration risk and then uncertainty of actually developing and accessing resources. And so we're doing this through developing new exploration technologies and methods. We're looking at the use of machine learning to help both identify new signatures for where hidden systems might be, and then also in another space that I'll talk about in a second for improving efficiency of our operations in the drilling space. So we're looking at drilling as a major contributor to lowering exploration risk because it comprises around 50% of total capital costs for geothermal projects in general. So when we think about how can we take less time to drill a well, or how can we reduce the material costs of any well, that makes a significant impact and lowers costs of the development significantly. So we're looking at this from an engineering side, from an efficiency side, using methodologies that we're translating from oil and gas. John McLennan is leading this space in our Forge project, where we are seeing absolutely tremendous advances that are really exciting. But we're also looking at it from a data perspective. How can we use machine learning, other things to improve prediction and detection of events that are going to take time and cost money? And then finally, one other piece that we're working on in this program is that critical material extraction, looking at how can we supply valuable critical materials using geothermal brines. And we actually have a prize focused on that right now. It just closed, but if you're interested in following along with how it progresses, there's a link and you can see that in the slide. I'll send these slides to John afterwards. So On to EGS. This is my subprogram, so I'll talk about it in a little bit more detail. But these are, conventional systems. As you could see, sort of when we looked at that map of where geothermal development exists today, Western U.S. in an area where the tectonic environment that's appropriate, where we have resources that have surface expression or that we've been able to find. But they are limited to specialized areas where all of those three needs are co-located: heat, water, permeability. But as I said earlier, there's heat in the subsurface no matter where you go, as long as you're willing to drill there. And I like this term of stranded heat because you can think of it like, well, if we can go utilize that heat for something else, we can make power from it. And so if we add water and we reopen existing pathways or make some new ones, and then collect that heated water, we have an EGS system. And so there's some really interesting numbers in terms of what our resources are. And this is an area that we need to improve on, and is our resource development or our resource assessments for EGS in general. But some assessments from the last few years have said around like less than 3 kilometers depth. So in the shallow subsurface, in the lower temperature area, the accessible EGS resource is around 800 million terawatt hours. And then if you look at 3 to 10 kilometers, it's around 3,600 million terawatt hours. And for context, it's, we're talking about 3,800 terawatt hours for the US, in general in 2020, utilized by the US in general. So this resource is insanely massive. Not all of this is obviously accessible. Some of that does exist on, national park land or things like that. But in terms of if we can drill to those depths, it is theoretically accessible. And even when you take out the areas that are public land that we can't access, the resource is still on the order of hundreds of gigawatts. So we want to access this massive resource, and we need to and we want to produce this clean energy from it. But in order to do that, we have to resolve some geoscience and engineering challenges, and this is why the ARMA community is so exciting to be partnering with over the last many years, because so many of our challenges are geomechanical challenges. But basically, if we want to create an EGS reservoir, we need to better understand what the subsurface looks like. So what the temperature, the permeability, the temperature, stress conditions, fracture characteristics, and we need to use that information to create accurate 3D geological and geophysical models. That helps us design simulations, and it helps us track the evolution of reservoirs over time, which is critical for making sure that they're economic. And as you all know from your fields, some of these things are not measurable. Some of these things are very challenging to measure in stress conditions, as an example, or what's happening in a fracture at 12,000 feet below our feet. So my program focuses not only on trying to develop the models, but also developing the technologies and methods that can help us actually get this data from the subsurface, or develop proxies for those things that we can't actually measure. So then the other piece of like the big critical need and challenge in EGS for it to become a commercial reality is being able to manipulate the subsurface. And there's obviously so much that we can learn and are learning from the oil and gas industry. But this repeatable control of the subsurface and ability to enhance permeability is critically important. And to do that, again, we need to understand the structural and geomechanical, geochemical environments. And then we have to design engineering solutions that can help us counteract the evolution of permeability when it's going in a non-economic direction. And so we're looking very closely at this, and looking very closely at the limitations of trying to do these things from an engineering perspective at 200+ degrees Fahrenheit, which is always the challenge. So again, as you can see, at least in the EGS space, very macro and micro scales. What's the rates of dissolution and dissolution and precipitation on our fractures? How are different fracture modes interacting in terms of what our permeability looks like? How can we actually track permeability accurately from using geophysical measurements? So there's a lot that we're still working on in the EGS space, but that being said, there is a tremendous amount of success so far in all of these spaces, and massive advances so far in moving us in the right direction. And I'll talk a little bit about opportunities for what we're doing right now in sort of the near term to get megawatts online from geothermal, from EGS. So in terms of our priorities, in terms of what research we fund in my program, we're looking at Forge, and Forge is what John is a major part of, and many of you may have heard about before. This is our largest initiative that's focused on enhanced geothermal systems, ways to create and sustain EGS reservoirs using, collaborating across industry, across various disciplines, to try and understand how to develop the most effective ways for this creation and sustainability. And then also to track the evolution of the reservoirs, as I said, which is critically important. We also know that zonal isolation is absolutely essential for EGS to work. And so we have some programs focused on R&D to develop tools and techniques that can function in the environments that are high temperature, pressure, and the caustic environments that we encounter in geothermal. And then finally, what I was just alluding to earlier, we're looking at sort of this nearer term EGS, which is operating in the margins of existing hydrothermal fields. And that is meant to show that EGS can work now, that especially if we use existing infrastructure, maybe an idle well or an unproductive well, we can turn it into something valuable by using EGS methods and techniques for stimulation. And we have a number of projects actually that are open in this space right now. We also have a FOA that you can see here on the screen, Wells of Opportunity on the right side, that's open for folks to apply. And we'd encourage you, if you're interested, this is doing exactly that. If you have a well that's on the margins of a hydrothermal field and there's an opportunity to develop more power from your field using EGS methods or using new zonal isolation and stimulation technologies, we are interested in making that happen. We also have another topic area here that is utilizing existing wells in hydrocarbon fields, which are basically potentially also an opportunity where there might be stranded heat to try to see if we can develop geothermal power. But I want to just go back to Forge for 1 second to say that, that this project is extraordinarily important in moving EGS forward. This is an over $200 million effort. It's the largest program that our office has ever funded. And it's focused, as I said, how to make EGS successful from a reservoir creation and sustainability perspective. But also we are looking at characterizing the Forge site in the most robust way that we can, probably the best characterized site, geothermal EGS site to date, and then making all that data available to the community. So just a plug for those of you who might be interested in looking for data sets. There aren't a lot of geothermal data sets that are public, and so a critical aspect of this is to disseminate technical data to the community to help inspire and foster new and new research on geothermal that might not even be part of our effort. So I'd encourage you to go to the Forge website. It's a really exciting project, and there's so much exciting stuff happening literally as we speak, and for the rest of the year. So quickly, I'll move into the low temperature program really quickly and just talk about, basically we're talking about anything that is shallow opportunities for geothermal use. So anything you can do below 200 degrees Fahrenheit. Heat pumps, as I said before, very low temperature, 40 to 80 degrees. Direct use, we can use direct use in a shallow environment or deeper direct use. This is something we're looking into right now. And then low temperature electric power, where we look at how can we use, on the order of 100 degrees or 150 degrees for actual power production. So USGS has estimated around 46 gigawatts of thermal heat that's available from low temperature resources in the US. And as I mentioned earlier, the opportunities in the direct use and the heat pump space is really tremendous for CO2 reductions and also just for resiliency of our systems. So in this program, we're looking to not only address the technology challenges that might exist for deep direct use specifically, and for improving efficiency of direct use in general, but we're also really focused and starting to be even more focused under this administration on awareness challenges. People don't know what direct use is, they don't know what heat pumps are, and we want to make people aware of the benefits that they provide. So we're looking at some feasibility studies for direct use. East of the Mississippi, actually, we have a project that's really exciting at Cornell University, and also looking at this other topic for energy storage, which is a really fascinating use, and it's still early stages, but the idea of converting electric energy from power plants and storing it as thermal energy in saline aquifers. So we have some work happening with a couple of different awardees. USGS is working on this, where we are looking at the feasibility of it, looking at what we could do with that stored heat, how you might use it, you basically withdraw it later for direct use applications. or even indirectly for electricity generation. So so finally, the data modeling and analysis subprogram. This is less technical, so and I know this audience is more in the technical space. So I'll just say here that what we're looking at is communication of the operational flexibilities, assessment of the environmental and the economic benefits of geothermal in general, and then all of that helps sort of underpin the direction that the technical programs in the office go. So we use the economic modeling and the environmental modeling. We look at how geothermal will fare amongst our sister renewables and in the general power sector and in the out years with grid models. And then we focus on technology advancements as a result of this analysis in our technical programs to try to meet those needs. So I want to just close by sharing the potential, which is the most exciting part of the talk. So the potential for both the heat and the power side. So I alluded to these at the beginning, but just kind of thinking about heat pumps and the opportunities that they provide for heating and cooling, especially in some really unusual conditions that we're seeing across the U.S. these days, from natural disasters, from just very the heat dome that happened in the western U.S. just last week or the week before. So the opportunity here to increase deployment of geothermal heat pumps from around 2.5 to 28 million, and I already talked about the CO2 emission reductions that could happen just as a result of that. And then district heating systems on the right side of the slide. We only have 23 existing, and we are far behind the international community in this space. And there's a really interesting opportunity to expand based on our modeling from our GeoVision study to around 17,000 in the US. And then from a power production standpoint, which is really exciting, a 26-fold increase in geothermal energy production, around 8.5% of total generation by 2050 from enhanced geothermal systems primarily, but contributions that you can see from the undiscovered resource as well. But the caveat here, and the note that I want to end on, is that technology innovation is absolutely essential to getting there. And a little bit of policy, but basically we need to better understand our subsurface conditions to reduce our risk. And we need to innovate and develop technologies that are going to help us operate in these challenging conditions more efficiently and in general in order to get there. So really, really important to keep focusing on technology innovation, and that's what our office will continue to do. And we'd love to have you all be involved in that, and love to hear your thoughts on this. We're very excited to be part of the solution at DOE and to be helping to see and grow the geothermal industry and drive this innovation to see deployment on these scales. So I think that's all from me. I have some follow-up slides if people are interested in our budget or in any other aspects, but I think I'll leave it there. Hopefully that's good timing.
That's fantastic, Laura. Really outstanding, and very, very exciting presentation. We do have a few questions. Do you want to go to the chat, or do you want me to?
Oh, sure. Let me check it out. Sorry, I wasn't noticing that. All right, forgive me if it's showing a block on the screen. I'm new to Zoom.
Well,
okay.
I can translate these. I mean, the first was from Grant Walk, and Grant had to leave, and I hope in his absence I'm not pronouncing his name incorrectly. But Grant, his question relates to seismic activity. How do you address concerns about seismic activity associated with geothermal developments?
Oh, sure. Thank you for reading that, John. I was just getting the chat box up. So yeah, this is a great question, and something that is sort of top of mind for us in the geothermal program, and frankly the international community as well. So the U.S. Department of Energy partnered with the Berkeley National Lab and the international community, IEA, back starting in 2012 to help develop a protocol for safe operations of enhanced geothermal systems. And so we have then since modified that protocol and updated it based on experience in the field, based on operations that are happening internationally. And that protocol guides the way that not only do we expect for enhanced geothermal systems development that are funded by Department of Energy are required to follow this protocol, but we expect that the industry in general, when EGS is commercialized by industry, to follow this as well as best practice. So it's focused on the important sort of engineering aspects of making sure that seismicity is being monitored and being tracked, and that there are mitigation protocols in place for if seismicity does occur. But it also covers a really important aspect of seismicity, which is focused on engaging the community and being open about and educating about seismicity. So this is a critical part of engaging your community, making sure that that there's sort of social license to practice is being taken into account as well. So we have been using these protocols since 2012 in the U.S. domestic EGS projects. John is familiar with this because he's had to abide by it in the Forge project, and it's been very successful. So the other point that I'll just raise is that the National Resource Council and National Academies did a study on subsurface energy technologies back, I think, 2014 or so, that looked at carbon capture, oil and gas production, geothermal, a number of other mining technologies that work in the subsurface, and the risk of seismicity. And one of the critical findings from that study is that the what you're injecting and removing has a much lower risk of seismicity than those that are injecting and not producing. And so geothermal alone was sort of lauded in that report as being the first to have a comprehensive protocol to manage seismicity, but also was benefiting from the fact that inherent in the operations of EGS and geothermal in general is that we're injecting and producing consistently. So I think it's a very fair point. It's something we absolutely need to be mindful of. European projects have been had a lot of attention on them as a result of seismicity, but it's important to note that we're paying very close attention. We're monitoring it. We are doing assessments of every site prior to operations to ensure that there is a very low seismic risk, and then knowing that the risk of seismicity is generally extremely low at those sites, then implementing these mitigation procedures. So hopefully that's helpful.
That's great. So Lauren, the next question came from Ed Sieberts, and he appreciated the presentation.
I have a question too.
Ed is interested in if you could discuss current and projected future costs of geothermal sourced power versus current conventional power supply methods. So something about cost.
Oh, sure. Well, I wish I could bring up the LCOE chart that I have very, very accessible somewhere. But so that's a great question. So EGS LCOE is on a much higher than current hydrothermal development right now. And so there's maybe I can provide a link to this report from our GeoVision, or this figure from our GeoVision. But we see the LCOE, levelized cost of electricity for hydrothermal operations, sort of ranging to a maximum of around $100 per megawatt, I think, and at a minimum of around at this point, I think around 50. And so we are in a range that in some cases is cheaper than some other options that exist. I think solar is just so dirt cheap right now that it's impossible to beat. But I think that the levelized cost of electricity is within a very, very reasonable range for hydrothermal, such that there have been a number of power purchase agreements that have been signed in the last few years, 9 since 2019, with these reasonable rates. But then, as I mentioned during my talk, it's kind of LCOE isn't really the best measure of the benefits that geothermal can provide, and so we're really interested in finding some other way that's comparable to the other technologies that are on the grid right now, to show those other benefits, the flexibility that geothermal can provide and the resiliency that makes it actually have a higher value. So forgive me I can provide a link with the exact costs, but it's within a range that's most certainly competitive in the hydrothermal space, and in some cases very low.
and we can get that to the audience, Lauren. So the next
That'd be
question, the next
And I was
question, so, well, we had an individual who's tried to ask a question. Why don't you go ahead? Oh, maybe became a little shy there. Okay, so the next observation and question came from Nico Roussel, and Nico once again appreciated the talk, and his question is about sedimentary geothermal systems similar to the DEEP project in Canada. What's the DOE's position on those?
Oh yeah, that's a great question. We're very interested in looking into this space, and one of the slides that let's see if I can go back to it. One of the slides I brought up with our current open funding opportunities covers this slide here, Reamplify. If you can see on the bottom right, this is the open solicitation right now, and we're specifically targeting sedimentary formations for to assess what the potential for geothermal production from these areas might be. So we're very closely following what's happening in Canada. We think that there's a really interesting opportunity and exciting opportunity to look into the space. I think that there is no doubt that new technology challenges will come from operations in sedimentary fields. It's not a direct one-to-one oil and gas translate to geothermal, even though we'd be working in much more similar geology than in working in the EGS space, where we're working in harder rocks and higher temperatures. I think there'll still be interesting new challenges for maintaining flow and permeability, but I think there's a really exciting opportunity that we're very interested in pursuing, especially for the low temperature power production space, and the opportunities for sort of direct use, and for the implications that can have on communities where there might be either existing wells that exist from previous hydrocarbon activities, or in cases where we would potentially in the future, not under this fellow, but drill new wells. What could the implications be for communities that are local to it? So I think it's a great and exciting area, and I love what Canada's doing in that space, specifically with community engagement.
So Lauren, the next question came from Ahmed Sarouche, and it relates to, well, I think one of your figures showed electric generation at 150 degrees Fahrenheit. So Ahmed is interested if the DOE has any plan to support technologies that are developing lower temperature organic Rankine cycle or similar.
Oh, sure. So, and John, thanks again for reading all these for me. You're so nice. I'm sorry that with two computers, I still can't access the chat appropriately. But yeah, so our office historically had a very large program on surface equipment and technology development for low temperature power production. That's not an area that we're currently working in, because we moved the technology forward, at least we felt, to a place where it was highly efficient, and the commercial entities were sort of taking on the future advancements. So it's not within my portfolio. This is my colleague Alexis's portfolio, so I don't want to speak for her future plans, but I would say that we have funded a significant portion of funding in the past 2009 to about 2014 in that space, and we're, as technology advances, it is interesting to see. I know that there are some new units and new things happening in some European companies where they're able to produce even more efficiently at lower temperatures. So it's certainly something we're paying attention to, but currently no funding is going towards technology development in that space.
Sophie Ann's question, Lauren, she has two. One, is there any program in offshore such as Hawaii? And the second question relates to the slide that you have up here now. Maybe you could reiterate about converting dry oil and gas wells to geothermal wells.
Sure. Yeah. And so Hawaii, I assume you mean actual power production on the Hawaiian Islands, not offshore geothermal, as in like in the mid-ocean ridges, etc. But I'll just speak to both really quickly. There are some really interesting ideas and proposals. If any of you have heard of the World Geothermal Congress, it's a meeting that happens every 4 years about geothermal. There have been some neat presentations on actual in ocean geothermal production. Obviously, there's a big resource there, but that's not something that we're looking at right now. And in terms of operations in island nations and Hawaii specifically, yes, there's we had historically had a project there under our hydrothermal program, looking at ways to assess new opportunities for development in Hawaii. So absolutely, there's tremendous potential there, and we'd love to see more development happen. And then in terms of Reamplify, forgive me, I just remembered your second question. This topic area is focused on getting a baseline assessment for what what proposers might be able to produce, either from a heat or a power perspective, from existing hydrocarbon fields. And so, we're targeting production on the order of 1 megawatt to 10 megawatts thermal, and looking at whether we can actually generate power or heat and show production, demonstrate production, I should say, at a specific field site, or whether we can do some preliminary testing to indicate what production could look like. Those are both allowable under this topic area of this FOA, and it's really an exciting first step into sort of collaborating and looking at how we can utilize existing infrastructure. Again, more heat that exists and more assets that exist that would lower the cost of development, hopefully, but yet put more power or heat online.
No, so HiCam has a question that may take a couple hours to answer, but it's a relevant question. I mean, can you give a high-level summary of how one would do a seismic risk evaluation?
Oh gosh, yeah, that would take a while. I would be happy to point you towards some existing induced seismicity mitigation plans that we require all of our projects to develop, as I mentioned. But the baseline is just at the highest level is we ask our teams to look at the structural environment. We want to know, are there any existing faults around? Are they active? What's the size? What's the surface area of the fault? What's the background seismicity in your region? And we usually ask people to monitor to the sub-zero level if they can. And Utah Forge is doing some really exciting and interesting things on their baseline seismic monitoring using new methods. Which is really interesting to note. So take a look at their website too. And then we ask for the teams to assess what is a probabilistic seismic hazard assessment. So what could happen at this site from natural, in terms of natural seismicity. And then we ask them to assess, well, what are you planning to do in terms of your injections? And then what does that look like from a modeling perspective? What might we see in terms of seismic levels, depending on the variety of injection scenarios you might propose? How would we mitigate if something happens at X, Y, or Z level? If we see an event that's a magnitude 1, what will we do? Reduce, stop flow, stop injection, flow back, yada, yada, all of these types of things. So we have a very, very comprehensive requirement that all the projects need to go through, but it spans, baseline structural geology, like history, seismic history, all the way to very advanced modeling on predictive modeling on what might happen. That was my short version.
Yeah, no, that was a great summary. James Rogerson found it a very interesting talk, and he appreciates you sharing it. And he's anxious if you could point him in a direction where he might be able to find something about the total cost breakdown in from exploration to facilities, spud to production and facilities.
Yes, so I would say the best place to go, the most comprehensive documentation that DOE has to date is in the appendices of this report at this link, which I will provide to John afterwards. And so this is our GeoVision, where we assessed all the scenarios of what could happen and what that would look like for deployment out to 2050. And so there were some very in-depth cost assessments using our economic model, get them to predict or to assess what current costs are and what costs could be based on technology improvements. So you could look at the baseline assumptions for hydrothermal and for EGS, and then what we are hoping that it could get to from in this report. If you take a look at the I forget, I think it's chapter 3, but don't trust me.
No, that's cool. And so Claudius has another question related to induced seismicity, and maybe we'll just forward some links with this presentation that you can provide us, Lauren, maybe sort of address some of those things.
Absolutely, yeah.
And then Lotana she's read a lot. She appreciates your presentation, and she's read a lot about the difference between heat transfer, convective heat transfer in EGS, and less efficient conduction in closed loop geothermal. And question is this something DOE considers in these projects, and are there DOE publications on the technical details of closed loop that one can look?
Oh yeah, great question. So I would say that in our demonstration portfolio that I mentioned, these near field EGS projects, we are focused on power production there, and so we're looking to to see power production on the order of a few megawatts. 5 megawatts is our goal from each project. The distinction with those projects, we have 3 underway right now, and Forge is a laboratory where we're looking to try to resolve some of the challenges that I talked about, the subsurface challenges, the geoscience challenges, and engineering challenges to moving EGS forward. So we're interested in what the potential power production could be from and I'm making this connection between heat transfer and in the Forge system, but we're not necessarily, at least the DOE is not forcing Utah to provide us with an assessment in that space. So we do consider, it varies in the Forge project, that's not necessarily our focus. From the closed loop perspective, though, you're absolutely right in terms of there's a hot debate right now in terms of the differences in heat transfer between closed loop and EGS because of the convection dominated systems, etc. We are running an internal study right now on this. We are. I think that I know that there will be some publications coming out in the annual Geothermal Resources Geothermal Rising conference that happens at the end of the year, because that project has up until now been an internal project, but we have asked them to start publishing their results. So we are taking a look at the technical details of closed loop and different modeling scenarios in which we wanted to get an assessment of how closed loop could operate in different environments. So take a look when that meeting happens. I think in November there'll be some publications, but those will be the first from the Department of Energy on closed loop.
That's all I have on the chat, Lauren. We've worked pretty hard here with the questions.
Thank you so much, John, for reading them. They're so kind. I really appreciate it.
And I think I can speak for everybody that we really enjoyed an informative and candid presentation, and we will make this available to all of the participants recording, and if somebody wants them, I presume the slides too. And so thank you all, and we'll see you in a couple of weeks for the next talk in the series from Professor Bazant.
Awesome. Thanks, John, and thanks again for all your help. I appreciate it. And I'll get you these slides right away.
Thank you, Lauren.
All right. Take care, everyone.
Bye-bye. Yeah, thanks, Lauren.
Thanks again for all your support from the ARMA community. Take care.